Welcome to the video lecture on the disk and washer method. In this video lecture, we're going to take our first look at volumes of revolution. When you take a region and revolve it around a line that does not cross the interior of the region, then the resulting solid is called a solid of revolution, and the line is the axis of revolution. So for example, suppose that we have this rectangular shape in the first quadrant and we rotate this using an axis of revolution of the y-axis. If I rotate that around that y-axis, it's going to flip over and have a sort of a mirror image on this side. And if you imagine taking a cross-sectional little slice out of this, that cross-sectional slice is going to have the shape of a circle because we're rotating this through 360 degrees. So we get these little tiny disc shapes for our different cross sections. And this shape in 3 dimensions would look like a cylinder. Now if we took a same rectangle but we shifted it over from that y-axis and we rotate it around the x-axis this time, then this is going to flip over down below the x-axis, and again we're rotating it through 360 degrees, so we're still going to get those circular cross-sectional shapes, but this time they're vertical instead of horizontal. So it's still going to have sort of a disc shape to it, if you will, with some thickness to it. Now this one, if we rotate it around the y-axis, what would that look like in 3 dimensions? Well, we can draw its mirror image over here, and if you imagine this spinning around 360 degrees, then this has sort of the look of a cup, but it's solid inside because we have that inside part completely filled in. So some kind of solid cup shape. Now let's visualize this one. If we rotate this shape around that y-axis, then the mirror image would show up over here, and again we'd get that circular cross-sectional shape. And this time it looks just like the last one we did, but it's sort of flipped upside down. So it's a solid upside down cup. Now if we take this more irregular shape and rotate it around that x-axis, what would that look like? Well, the mirror image would come down here, and to me this looks kind of like a vase shape on its side, but again it's going to be solid in the middle, so this would be sort of a solid vase on its side. For the next one, we have this sort of almost triangular shape, but it's rounded, and if we rotate that around the y-axis, then the mirror image would look like this over here. And this time it's not solid throughout because we have sort of this hole in the middle. So this would look more like a bowl shape, like a soup bowl, because you have sort of this rim, which is this region right here, and then you have that empty hole in the middle. So to me this would look kind of like the rim of a bowl. And then for this last one, to help us visualize these, if I rotate this around the y-axis, again we have this hole in the middle, and if I rotate this around, these circular shapes inside here are going to have a hole in the middle. So what would this look like if we flipped it around 360 degrees? To me that would look more like a really thin tube, like a paper towel roll, if you will, where there's a thickness in the rim of it, in the shell of it right here, but there's that empty hole in the middle. So to me this would look kind of like the rim of a paper towel roll. So these examples here are just meant to help you to start visualizing. This is going to be very graphical that we do here, and you're going to really need to draw pictures and visualize what's going on. Now what makes all of these examples similar is that in each example, when we rotate this 360 degrees around our axis of revolution, that means that our cross section is always in the shape of a circle, what we call a circular disc or discs. And since the area of a circle is pi r squared, then the area function that we can use in our volume integral is just going to be a equals pi r squared. So for example, if we take that rectangular shape, rotate it around the y-axis, and visualize this spinning around, we're going to get that cylinder shape. If I take a cross-section slice It's going to have the shape of a circle, and I'm going to give it a little bit of a thickness to it. So that's what's called a disk, when it has a little bit of a thickness to it. So it's a three-dimensional circle with a very small thickness to it. Now, since that disk is perpendicular to the y-axis, it's going horizontal, and that thickness is intersecting that y-axis, we're going to let this thickness be called delta y. So it has some small thickness to it, and the area of this cross-sectional shape, because it's a circle, is that pi r squared. So to get the little tiny amount of volume, which I'll call delta V, in this little tiny disk, it would be the area of that shape, which was pi r squared, times its thickness, because volume is area times height, or area times thickness. So if you take each of these little tiny disks and add them all up, and we're going to have a whole bunch of them throughout our little cylinder shape. If I add up all of those little volumes in all of those little disks, then that is going to give me an approximation to the true volume. And what I could do in terms of calculus is let that thickness get smaller and smaller and smaller and go to 0 in the limit. And what that does is it turns this accumulation, or this sum of these volumes, into an integral. So this delta V turns into just V, and this pi r squared delta y turns into the integral of pi r squared dy. So if you take your cross sections perpendicular to the axis of revolution, and it's a vertical axis like this, then we're going to get those dy's, and you're going to get a dy integral. Now, if we have a shape that's being revolved around a horizontal axis of revolution like the x-axis, then this is going to flip down over here, and this time if I take my cross sections perpendicular to the axis of revolution, since this axis is horizontal, I want my circles, or my cross sections, to be perpendicular to that, so that means they're going to be vertical. So my little disc shapes would be going up and down, and they would again have some thickness to them. But this time that thickness is intersecting the x-axis, so that would become delta x, which means our little volume slices, and there's going to be a whole bunch of them here, these little circular discs, each have a volume of pi r squared times delta x. And as I let that thickness delta x go to 0, this turns into an integral and becomes volume equals the integral of pi r squared dx. So if your cross-sectional slices, or your circles, are vertical, then you're going to end up with a dx integral. If your cross-sectional circles or discs are horizontal, you're going to have a dy integral. So the rule of thumb, this is what you want to sort of memorize about this, is that when you're using what's called the disk method, which is what we're talking about here, you're always going to take your cross-section cut perpendicular to the axis of revolution. So if you have a vertical axis of revolution, like the y-axis for example, then your disk should be horizontal, which means you are going to have thickness along the y-axis. So this is going to be a volume integral, which has as its formula the integral of pi r squared dy. So this is basically a formula that you would just plug into. And this r is going to be a function of a variable, and since we're using dy here, this r needs to be a function of y. So whatever you plug in for what this r turns out to be, it needs to be using the y variables, and the bounds that we have on our integral need to be bounds for y and how y changes. So everything in this formula should be in terms of y's. If we have a horizontal axis of revolution, then when I go perpendicular to that horizontal axis, then my cross-sectional cut is going to be vertical instead of horizontal. So that means we're going to get this vertical disc shape. And that means the thickness is along the x-axis. So now we want to be thinking in terms of dx. So the formula for a horizontal axis of revolution is going to be volume equals the integral of pi r squared dx. And whatever you come up with for your radius function, it should involve x variables only, And the bounds on this integral should be how the x changes only. So these are basically two formulas that you're going to use when you have a disk shape as your cross-sectional cut. Okay, so let's practice this. Find the volume of the solid of revolution formed when the region bounded by y equals 4 minus x squared, x greater than or equal to 0, and y greater than or equal to 0 is revolved about the x-axis. So these are pretty visual. You definitely need to draw yourself a picture. That's going to be very, very key. If you need to use a calculator, that's fine. This one for me is easy enough that I can probably do it by hand. So if I have the function y equals 4 minus x squared, that's a parabola that points down because the x squared is negative, and it's shifted up 4 units by that plus 4 in front. So this is just a parabola that hits at 4 on the y-axis and goes down. And it's hitting on the x-axis at wherever y is 0. And if you let y be 0 and solve that equation, you'll see that x would be plus 2 or minus 2. So this is hitting at 2 and minus 2. Now notice that they are also telling us to use this curve, but also use x greater than or equal to 0, which would just be the right half of the x-axis, and y greater than or equal to 0, which would just be the positive y-axis going up. So this is really just quadrant 1. So we're restricted to quadrant 1 here, which means we actually don't want that left-hand piece of the curve. We want the region bounded by these three things, and the region bounded by this parabola in quadrant 1 only is just this right half. So this is the first region you start with. Now what we're going to do with this is we're going to rotate it around the x-axis. So what I always recommend doing is first drawing in that mirror image. So if I have this quadrant 1 little region and I flip that around the x-axis, then the mirror image down here is going to look like this. The next thing I recommend doing is drawing in your cross-sectional disk. Because our axis of revolution is the x-axis, which is horizontal, my disk should go vertical. It should always go the opposite or the perpendicular direction. So I want to draw in a disk that is vertical, just like this. And I like to give it a little bit of thickness to represent that disk shape. Now, because it's going vertical like this, that immediately tells me what formula to use. Since this is a nice solid disk shape, then the disk method, and this disk can be written with a K or a C, I kind of interchange the two. The disk method formula is volume equals the integral of pi r squared, and since this is vertical, so that it's intersecting that x-axis, this thickness is along the x-axis, so this is going to be a dx integral. So that means we want to determine our bounds in terms of x and this r, this radius, in terms of x. So let's talk about the radius first. What do you need to know to get the radius of this disk shape? Well, the radius would be the distance from the center of this circle out to the rim of the circle. So this distance right here. So here's what I recommend to students. Look and mark these 2 points, the center point and the point on the rim, and find their 2 coordinates. What you'll notice is that since they're vertical or right on top of each other, they both have to share that same x coordinate. I don't necessarily know what it is, but they both have the same x, whatever that is. So I'm going to write down the same x for both of these 2 points. The y's are obviously different because these 2 points are at different heights. Now this point on the center is always going to be along that x-axis, and the height at the x-axis is always 0. So this y coordinate must be 0. What about the y coordinate of this point on the rim? Well, depending on where you draw your disk, I could draw another disk over here. and then that rim point would be down here. What's the same thing about these 2 points? What do they share in common? Well, they don't have the same y value, but they both are on this curve. And what is the equation of that curve? It's y equals 4 minus x squared. So the y coordinate of this point is this y. But I don't want y's, because remember, this is a dx integral. I want to know what y is in terms of x, which is exactly this formula right here. So for the y coordinate, I'm going to write down the formula of that curve for what y is in terms of x. So now that you know the coordinates of these 2 key points, then the radius is going to be the difference in these 2 heights, which is the difference in these 2 y coordinates. And in order to ensure that you're getting a positive distance, you always want to do the top point minus the bottom point. So we want to do the top y value, which is 4 minus x squared, minus the bottom y value, which is just 0. So that means the radius function that I want to use is 4 minus x squared. And we're going to take that and we're going to put that right over here. So this formula for volume becomes the integral of pi times this radius function squared dx, because you want pi r squared dx. Don't forget to square your r. Now the last thing I need here are some bounds. Since this is a dx integral, we want to look at how x changes, and my x's range from 0 up to 2. That's this distance that I cover along that x-axis. So my bounds should be from 0 up to 2. So there's my volume integral. Now all I have to do is actually integrate it. Okay, so in order to integrate this, unfortunately we can't use pattern recognition. If you have this outer power of a square, you would sometimes call this inner function g, and unfortunately we don't have the correct g prime. We would need a negative 2x in order for this to work for pattern recognition. So my only other alternative would be to go ahead and square out this quantity and then integrate term by term. Now that pi isn't really helping me at all, so what I would recommend is pulling that pi out, get it out front and out of the way, and then let's go ahead and square this quantity. Remember to FOIL. So we're going to get a 16. In the middle, we're going to get a negative 8x squared, and then on the end, we're going to get a positive x to the 4th, and we want to integrate each of those. So the pi stays out front, and this becomes the integral, or the antiderivative of 16 is 16x. The integral of 8x squared becomes 8x cubed over 3, and the integral of x to the 4th is x to the 5th over 5, and now we can plug in our bounds. I'm going to leave that pi out front, and I'm going to use brackets here. When I plug in the when I plug in the 2, I'm going to get 16 times 2, which is 32, minus 2 cubed, which is 8. 8 times 8 is 64, so this is 64 thirds. And then 2 to the 5th is 32, so this will be 32 fifths. And then from that, I'm going to plug in my 0 and subtract from that. Now when I plug in 0, all 3 of these become 0. On your calculator, I would just recommend plugging in 32 minus 64 thirds plus 32 fifths, and you can even use that fraction button to turn it back into a fraction. This turns out to be 256 over 15 times that pi, and you can just leave that pi in your answer. And there's our solution. Okay? All right, let's try another one. So now we want to take that same region that we had before, which again was the quadrant 1 region, that was that parabola pointing down, starting up at a height of 4. Okay, so we want to take this region, and this time we want to rotate it around the y-axis. So step number 1, draw in your mirror image. So if I take this region and I flip it over that y-axis, the mirror image is going to be over here. Step 2, draw in your cross-sectional disc shape. Now our axis of revolution this time is vertical, So our cross section should be horizontal. So my disk is going to go horizontally like that. And you could draw one down here, you could draw one up here. They're going to be different shapes with different radii depending on where you are on that little curve. Okay, so what do I want to do next? Well, look at the orientation. Since this is a horizontal disk, its thickness is along the y-axis. It's intersecting that y-axis. So the formula that we want to use is volume equals the integral of pi r squared, and it's going to be a dy integral because it's going horizontally. So this radius function that I come up with should be in terms of y's, and my bounds should be in terms of y's as well. So the next thing we need to do is figure out what that radius is. So pick one of these disks, it doesn't matter which one, mark the center point and a point on the rim. Now you could go to the right or to the left. I always recommend to students going back towards the original curve, not towards the mirror image. It just helps avoid confusion. So I'm going to pick the rim point on the first quadrant side instead of in the quadrant 2 side. If I want the radius, that's going to be this horizontal distance going across. So I need to know these two coordinates. Now notice this time, these 2 points are both at the same height, which means they both share the same y coordinate. So I'm going to label the y's as just y. I don't know what that height is, but it's going to be the same for both of those, whatever it is. Now for the center point, that center point for all of these different disks is always going to be on that y-axis, which means the x coordinate is always 0. So this x value is 0. The x value of this point is going to vary depending on where I am on this curve. What all these side points share in common is that they all lie on that curve y equals 4 minus x squared. Now in the last example we could just use this formula because it was already in terms of x's, but we want to know what x is in terms of y because this is a dy integral. I need to know what x is right here in terms of y. So that means we're going to need to solve this for x. So what I could do is add the x squared over to the left side and subtract the y, and then I can take the square root of both sides. Now when you take a square root, you get a plus or a minus case. Since we are in quadrant 1, originally on this right-hand side, that's the positive square root. The minus would be the left-hand side or this mirror image over here. But we're talking about the point on the right. So the x that we want to use right here should be the positive square root of 4 minus y. So my radius function will be the difference in these two x coordinates. So this x minus this x. And to ensure that you're getting the right orientation and a positive radius, always do right minus left. So we're going to take this right x value and we're going to subtract this x value, the left one, which was 0. So my radius function is square root of 4 minus y. Okay, so now that's going to be what we use for this r right here. So this volume integral becomes the integral of pi times, and instead of r, I'm going to use square root of 4 minus y, and then we want to square that radius. So there's my pi r squared, and now we need some bounds, and these need to be y bounds. So what's the lowest y and the highest y that I use? Well, the lowest y, I go down to that x-axis, which is a height of 0, and I go up to this height of 4. So my bounds for y are 0 to 4. So this is going to be my integral. Now to actually solve it, let's go ahead and square away that square root. And while I'm at it, I'm going to pull the pi out front because it's a nuisance to kind of keep it in there. So in this example, we get a little lucky because the square and the square root cancel each other out. So we just get 4 minus y. And that's fairly easy to integrate. The integral of 4 is 4y, and the integral of y is y squared over 2. And now if I plug in my bounds, 4 times 4 is 16. 4 squared is 16 divided by 2, which is 8. And then I'm going to plug in 0, which is going to make both of these become 0. 16 minus 8 is 8, so this becomes 8 pi. Okay? These volume problems take a lot of practice, and again, they're very heavy on the graphing and drawing pictures and labeling all of your coordinates, so it takes some practice to get used to that. Let's take a look at the next example. Find the volume of the solid of revolution formed when the region bounded by y equals x squared, y equals 0, and x equals 1 is revolved about the x-axis. Drawing that initial region is really, really key, because if you start off with the wrong region, then obviously you're going to get the wrong volume once you rotate it. So let's make sure that we're drawing the right region here. We want y equals x squared, which is a parabola that goes up to the right and up to the left. Y equals 0 is the horizontal line, which is the x-axis, and x equals 1 is just a vertical line at a height of 1, or at a distance of 1. So what region is bounded by all three of those? That's this region right here, so we don't need this left-hand side of that parabola. So I'm going to take that away so that it doesn't confuse us. So the region bounded by all three of these curves is that sort of triangular region. And what we're going to do is we're going to rotate this around the x-axis. Okay, so step 1, draw in your mirror image. So when I flip this down, the mirror image is going to look something like that. Step 2, take your cross-section perpendicular to the axis of revolution. My axis is horizontal, so my cross-section should be vertical. So we should be drawing circles that are going up and down. Because that circle is vertical and it's intersecting that x-axis, right away I know that my volume is going to be the integral of pi r squared, and this is going to have to be a dx integral. The next step, find your radius by finding your coordinates. So I want the center of this circle and the rim of that circle. I want to find those two coordinates so that I can subtract their y values to get that height right there, which is going to be my radius function. Now, since these 2 points are right on top of each other, they both have in common the same x coordinate. I don't know what it is, but it's the same. So I'm going to write this as x and x for both of these. They have different y values, however. The one on the center is right along that x-axis, so its height is always 0. The one on the rim is always going to be on this curve. It's going to follow the rim of this curve. So its y value is going to be whatever y is in terms of that function, which is y equals x squared. And remember, we want everything in terms of x. So the y value is just going to be whatever x squared is. So my radius function will be this top y value minus the bottom y value. You want to do top minus bottom. So this height minus this height would just be x squared minus 0, or x squared. All right, now we have the right pieces, so we can plug in. My integral becomes pi times this radius function squared, so x squared squared. And then what are my bounds for x? Well, x starts over here at 0 and it goes to that 1. So my bounds are going to be from 0 to 1. So to integrate, let's pull out our pi. X squared squared is x to the 4th. And when I integrate x to the 4th, that just becomes x to the 5th over 5. And we want to plug in our bounds. So that's going to be pi times 1 to the 5th over 5 is just 1/5. 0 to the 5th over 5 is 0. So this is going to be pi over 5, or 1/5 pi. Okay? Next example, take the same region in the last example. So that was the region that was our x squared and x equals to 1 and y equals 0. So that little triangular region. And this time we're going to rotate it around the line x equals 1. So x equals 1 is a vertical line. and it's this line right here, and we're going to rotate it around that line. So this time we're not rotating around one of our major axes, the x or the y axis. This time we're shifting over a little bit. So that's going to make things just a tad bit tougher to do. So step one, draw in your mirror image. So if I take this region and I rotate it around that line, x equals 1, the mirror image is going to look like this. Step two, draw in your cross-sectional cut perpendicular to the axis of revolution. My axis is vertical, so my cross-section should be horizontal. So I should have a horizontal circular disc going across like that. Now notice the thickness of that disc is horizontal along that y-axis. Even though my axis of revolution isn't the y-axis, it still would sort of intersect that. It's perpendicular to that y-axis. So this is still going to be a dy integral. So my formula is going to be the volume equals the integral of pi r squared dy. So whatever I come up with for my radius function, it has to use y's only. Next thing I'm going to do is I'm going to find my coordinates. I need the center of my circle, and then I need a rim point. Now you can go either to the left or to the right. I always recommend going back to the original region, which was this piece on the left side over here. Don't go to the mirror image, go back to the original side. So I need to know this point and this point. And then the difference in those two x's is going to give me this horizontal distance, which is my radius. Now notice those 2 points. They're at the same height, so that means they share the same y coordinate. So the y's are going to be the same. So I'll call them both y. Now let's look at this center point. What is the x value of this center point? Since it's on this axis of revolution, which is always x equals 1, then this x coordinate will always be 1. What's the x coordinate of this point over here? Well, that's going to be determined by this curve. And remember, our curve was y equals x squared. So I need to know what x is in terms of y. So I need to solve this for x to tell me what that x should be, but in terms of y's. So let's solve this for x by just taking a square root. Remember, when you take a square root, you get a plus or a minus sign. And originally this parabola, we had 2 halves to it. If you recall, we took away one of them. When I originally draw x squared, you get the right half, and then you get the left half over here. And we only used the part in quadrant 1. Now this side is the positive square root. This side would be the negative square root. And since we're in quadrant 1, we just want that positive square root side. So this is just going to be plus square root of y for this x value. That's what x is on this part of the parabola. Okay, so now that I know what my 2 x's are, to get the radius is going to be the difference in these 2 x's to get that horizontal distance. And to ensure that you're getting a positive difference, always do the right point minus the left point. So this right x value minus this left x value. So that's going to be 1 minus square root of y. Notice that this radius function is no longer just in terms of that function, because we have this 1 involved. We shifted it because we had a new axis of revolution at 1. So whenever your axis of revolution isn't one of the major axes, the x or the y axis, then your radius function is going to be shifted as well due to that new axis of revolution. So it's going to be a little bit of a translation going on. So we're ready now. Since we know what that radius function is, let's plug it in. So this r is 1 minus root y, and we want to square that. And then what are the bounds for y? Well, we know that this is starting at 0, and we need to know how high it goes. So how high is this point up here? Well, remember, this was the curve y equals x squared, and we intersected it with the line x equals to 1. So when x is 1, how high is this point on the corner there, well, when x is 1, 1 squared is still 1. So this is up at a height of 1 as well. So the y's range from 0 up to 1. So those are going to be my two bounds. So now to integrate, let's pull out our pi. And I'm going to go ahead and square this quantity out. So 1 squared stays 1. In the middle, I'm going to get a minus 2 square root of y, and then a square root of y times a square root of y, it becomes a positive y. To integrate this, I'm going to change this square root of y to a y to the 1/2, just to make it into a power, so it's easier to use my power rule. So the antiderivative of 1 is just y. The antiderivative of y to the 1/2 would be y to the, you add 1, so this becomes 3/2 times 2/3 times that 2 that was already there. So 2 times 2/3 is going to make this become a 4/3. And then the integral of y is y squared over 2. And we want to plug in our two bounds. So if I plug in 1, I'm going to get 1 minus 1 to the 3/2 stays 1, so this is just that 4/3 out front, and 1 squared over 2 is a half. When I plug in 0, each of these three becomes 0. So 1 minus 4/3 plus 1/2, all of that turns out to be 1/6 when you get a common denominator, so this final answer is just pi over 6. Okay? All right, let's try another one. Find the volume of the solid of revolution formed when the region bounded by y equals x to the 2/3, y equals 1, and x greater than or equal to 0 is revolved about the y-axis. So first thing you want to do is sketch your region. Now if you need your calculator to show you what this region looks like, that's fine. X to the 2/3 looks something kind of like this in quadrant 1, and I'm only going to look at quadrant 1 because I know that I have to have x greater than or equal to 0, and y equals to 1 would look like that horizontal line going across. So x greater than or equal to 0 would be that vertical line going to the right, and we have y equals 1, and then we have our curve, so the region bounded by all three is this sort of triangular shape right here. So what we want to do first is rotate this around the y-axis. So let's draw in our mirror image, and then let's draw in our cross-section. Our axis of revolution is vertical, so our cross-section needs to be horizontal, so your disc shape should be going across that y-axis and intersecting that y-axis. So that means the thickness is along the y-axis, so this is a dy integral. So this is going to be volume equals the integral of pi r squared dy. So let's find our coordinates. My center point of my circle, and then the original region was the one in quadrant 1, so I'm going to use this rim point on the right. So let's find these two coordinates. They're both at the same height, so they both have the same y value. The center point is on the the y-axis, so the x value is always going to be 0. This rim point is always on this curve right here. So we need to use the curve. And remember, we want everything in terms of y's. So that means we're going to need to solve this for x to find out what this x should be in terms of y variables. So how do you solve this for x? Well, we'd have to get rid of that 2/3 power. So what I could do to get rid of a 2/3 power is raise both sides to the reciprocal power. So that would make 2/3 times 3/2 go to 1, so we just get our x, and then the left side becomes that y to the 3/2. So x is y to the 3/2. So now I know my two x values in terms of y's. So the radius function is going to be the right x value minus the left x value. So y to the 3/2 minus 0 is just y to the 3/2. So let's substitute that in. We're going to take pi times y to the 3/2, square that, And then what are our bounds for y? Well, this region starts at a height of 0 and it goes up to this horizontal line, which was y equals 1. So my bounds for y are 0 to 1. So to integrate, let's pull out our pi. Y to the 3/2 squared is a power to a power, so you multiply. Whoops. So 3/2 times 2 is just 3. So this is going to be y cubed. And the integral of y cubed is y to the 4th over 4. And when I plug in 1, I'm going to get 1/4. When I plug in 0, I'm going to get 0. So this is just pi over 4. Okay? All right, the next example is the same region, but we're going to rotate it around the line y equals 1 this time. So let's draw our original region. We had that x to the 2/3, y equals 1, and then the y-axis, and we're rotating it around this horizontal line, y equals 1. So when I flip this over, its mirror image is going to look something like that. So when I take my cross-section perpendicular to this horizontal axis, perpendicular to that would be vertical. So my circle should look like this. And it's vertical, so eventually here you can imagine it's sort of perpendicular to that x-axis. So that means the thickness is along that x-axis. So this needs to be a dx integral. So the integral of pi r squared dx. Let's find our points. We need the center of the circle and then the edge of the circle. Remember that the original curve was the one below the line y equals 1. So I'm going to go down here instead of up to that mirror image. And I want this vertical distance right here. So I need to know this point and this point. They both have the same x value because they're both over the same amount. So both of these are going to have the same x. The center point is always lying on that axis of revolution, which is at a height of 1. So its height is always 1. The bottom point is always lying on this curve, and remember the curve was y equals x to the 2/3. So the y value is just this function right here, and we want it in terms of x, so this is perfect. I don't have to do any extra solving. So we have our two y's. We can get our radius. You want to do the top y value minus the bottom y value. So we're going to take the 1 minus the x to the 2/3. So just as in one of our previous examples, when your axis of revolution is not the x or the y axis, which would be either x is 0 or y is 0, your radius is a little bit more complicated. It has that shift in it. Normally your radius would just be your curve, but because our axis of revolution is shifted to y equals 1, that 1 comes into play in that radius. So let's substitute in our radius function. So the radius is 1 minus x to the 2/3, and we want to square all of that. And then what are my bounds? Well, again, this is starting at 0, and I need to know how far over I go. And the only thing I know is that this was that curve x to the 2/3, and it's where it intersects the line y equals 1. So if this is the curve y equals x to the 2/3, when does x to the 2/3 hit 1? Where do they intersect? Well, when you raise both sides to the 3/2, 1 to the 3/2 is still 1. So this is also hitting x at 1 as well. So it's just the intersection of our two curves that we had. That's determining our bounds for x. So here's my volume integral. We're ready to integrate. I'm going to pull out my pi. And I'm going to need to go ahead and square this out again. So 1 squared stays 1. In the middle, we're going to get a minus 2x to the 2/3 plus x to the 2/3 times x to the 2/3. When you add those powers, that becomes x to the 4/3. And now we need to integrate each of those term by term. So the integral of 1 is x. The 2 stays put. And when I integrate x to the 2/3 and I add 1 to that, 2/3 plus 1, or 2/3 plus 3/3 is 5/3. times the reciprocal out front. So this is going to become a 6/5 out front. Plus, when I add 1 to 4/3, 4/3 plus 3/3 is 7/3 with the reciprocal out front. And then we're going to plug in 0 and 1. So I'm going to get a 1 minus 6/5 plus 3/7. And when I plug in 0, I'm just going to get a bunch of zeros. I'll leave the arithmetic to you, but again, getting a common denominator, you can do all of that on your calculator very easily. This becomes 8/35, and then that pi stays put. So there is my volume. Okay, the next example. On this one, we want to find the volume of the solid of revolution formed when the region bounded by x equals negative y squared plus 4y, y equals 1, and the y-axis below the line y equals 1 is revolved about the y-axis. Okay, so this one's going to be a little bit tougher because the original curve that we're starting with is not a normal y equals something in terms of x. It's x equals something in terms of y. What you want to notice about it is that it is a parabola because it's got that y squared in there, but it's a sideways parabola because it's the y that's being squared instead of the x. Now, one thing that I like to note about these if I'm trying to graph them by hand is I go ahead and I look for the zeros. So if you take this x and let it be 0, when does negative y squared plus 4y equal to 0? Well, I can pull out a y, and that'll leave me with a minus y plus 4. So that's going to equal 0 when this y is 0, or when negative y plus 4 is 0, which happens when y is 4. So what that means is that in terms of my graph, this is a sideways parabola that hits the y-axis at 0 and 4. So 0 and 4. And because the y squared term is negative, this is a sideways parabola that points to the left. So it's going to have something like this for the top half and the bottom half. So that's what we're talking about for that graph. Okay? Then y equals to 1 would be down here. The y-axis would be here. And we want just the region bounded by these three curves that lies below the line y equals 1. So the part of this parabola that's below y equals to 1 would be just this part here. So we don't want this top part. So I'm going to erase it to kind of get it out of the way so we're not too confused. So we have our little piece of our parabola right here. Here's the y-axis and here's y equals 1, and all of that is below y equals to 1. So that's the region that we're starting with. And what we want to do with this is we want to revolve it around the y-axis. So we want to flip it over this way. So let's draw in the mirror image. So it's going to come over here. The axis of revolution is vertical, so my cross-section should be horizontal. So I'm going to have a circle that goes horizontally like this, which means it's intersecting that y-axis. So this is going to be a dy integral, pi r squared dy. Now let's find our coordinates. We want the center point, and I'm going to go to that original curve which was over in quadrant 1, and I'm going to find this horizontal distance. So I want that point and that point. Notice that they're both at the same height, so they both share the same y value. The x value of the center point, since it's on that y-axis, is always 0. The x point of the rim is always on our curve, and x is all of this in terms of y. So right here where I would normally put x, I'm actually going to put negative y squared plus 4y. And that's good news for us because we want y's. We don't want x's. So my radius will be this right x value minus this left x point. So right minus left gives me negative y squared plus 4y minus that 0. So my radius is negative y squared plus 4y. So now we're ready to substitute it in. This is pi times negative y squared plus 4y quantity squared dy. And what are my bounds for y? I'm starting down here at 0 and I'm going up to that line y equals 1. So y ranges between 0 and 1. To integrate, we pull out our pi, and I'm going to go ahead and square this out again. Negative y squared times negative y squared becomes positive y to the fourth. In the middle, we're going to get a minus 8y cubed, and then 4y times 4y is 16y squared. So when I integrate, I'm going to get for my antiderivative y to the fifth over 5 minus, this will become 8y to the fourth over 4, but 8 over 4 reduces to a 2. So let's just change that to a 2. And then 16 stays put and y squared becomes y cubed over 3. If I plug in my 1, I'm going to get a 1/5 minus a 2 plus a 16/3. And if I plug in a 0, I'm just going to get a bunch of zeros. So getting a common denominator and simplifying, 1/5 minus 2 plus 16/3 is 53/15. Use your calculator for that. So this is just 53 pi over 15. Okay? All right, same region, but this time we're going to revolve it around the line y equals to 1. So our region was that little tiny piece of that sideways parabola up until we hit the line y equals 1 and then the y-axis. And this time we're revolving this around the line y equals 1. So when I do the mirror image and I flip this over, the mirror image is going to be over here. My axis of revolution is horizontal, so my circular disc should be vertical. My cross-section is perpendicular. And that's vertical, so it would be intersecting that x-axis. So this is going to be a dx integral. So let's find our points. We need the center point, and then I'm going to go back to the original piece of the curve, not the mirror image, and I'm going to find this guy as well and find that vertical distance in between them. These 2 points share the same x value, so they're both going to be x comma something. The center point is always on that line y equals 1, so its y value is always 1. The y value of this point is going to be determined by where I am on the curve. And remember that curve was x equals negative y squared plus 4y. So we need to know what y is, but because this is a dx integral, we need to know what y is in terms of x's. I can't just put a y here. So that makes this one a little bit tough to do because we would need to solve this for y. And that's not so easy. So here's what we're going to do. We're going to need to do a little completing the square. Everybody's favorite thing to do, right? So the first thing I'm going to do to make completing the square easier is I'm going to get rid of this negative in front of that y squared by multiplying everything through by a negative. So this would become a minus x equals a positive y squared and a minus 4y. Now, what I want to do when I complete the square is I want to turn this right-hand side into a quantity squared. And in order for it to have a y squared and a minus 4y, I would need a y and a minus 2, so that if I were to FOIL this out, I'd get back a y squared, I'd get back a minus 4y in the middle, but I'd also get a plus 4, which I don't have. So I'm going to add 4 to the right, and I'm also going to add 4 to the left to balance it out. So these 3 terms now do factor correctly, and the left side is now this 4 minus x. Now the reason why we complete the square is because once it's in this squared form, we can take the square root of both sides. Remember, you get that plus and that minus case when you do that square root. And now the right-hand side just becomes y minus 2. And so to finish it off, I'm going to add 2 to both sides. So this becomes 2 plus or minus square root of 4 minus x is equal to y. Now what we have to be careful about here is which sign is the appropriate one to use. Remember, this parabola was a sideways one. The bottom half is the minus case, and you can verify that on your calculator. The top half of the parabola is the plus case. So since we're using the bottom half of our parabola, we actually want the minus sign. So that's a little bit tricky, but you can verify looking at the graphs to see that we really do want the minus case to get this lower part of the curve, this little blue piece that I have right here. So this bottom y value, this y will be 2 minus square root of 4 minus x. So now that I have my two y coordinates, oops, I want to get this vertical distance, that radius function, which is going to be the top y value minus the bottom y value. So this is going to be that 1 minus all of this, and use parentheses around it because we do need to distribute that negative. So this is going to become 1 minus 2 plus square root of 4 minus x, which becomes negative 1 plus square root of 4 minus x. So that's what our radius function is going to be over here. So this one has a complicated radius function because our axis of revolution was not one of the major axes, so we had that 1 involved, plus we had a complicated curve which we had to solve for y in terms of x, which got a little messy as well. So let's substitute in our radius function. So this radius function is negative 1 plus square root of 4 minus x, and we want to square all of that. And then what are my bounds for x? Well, this goes from 0, obviously, to where that x to the, or where that curve, that x equals negative y squared plus 4y, hits 1. So where does this hit? That's also not an easy question to answer. Okay, remember our curve. We have this parabola right here, which is x equals negative y squared plus 4y. And we want to know, when does it intersect y equals 1, which is this curve right here. So what is this x value? Well, to figure that out, plug in 1 for these y's. So we would get x equals negative 1 squared plus 4 times 1. The negative is on the outside, so you square just the 1, but the negative will stay put. So this becomes negative 1 plus 4, which is 3. So this is hitting over here at 3. So this is 3 right here. So my bounds for x are 0 to 3. Okay? All right, so this is a yucky one. Now we're ready to start integrating, and that's going to be yucky to do as well. Let's pull out our pi. When I square this out and FOIL it out, negative 1 squared becomes positive 1. In the middle, I'm going to get a minus 1 times the square root of 4 minus x, and then another one of those. So I'm going to get a minus 2 square root of 4 minus x, plus I'm going to get this square root squared, which is just going to give me that stuff underneath. Let's combine a few like terms here really quick. 1 plus 4 is 5, and then I've got that minus x and that minus 2 square root of 4 minus x. So the antiderivative of 5 becomes 5x. The antiderivative of x becomes x squared over 2. That minus 2 is going to stay put. And now let's think about the integral of the square root of 4 minus x for a moment. I just pulled that 2 out front. So that's going to stay put. How would you integrate this? Not so easy to do. Let's change that square root to a 1/2. And this can be done with pattern recognition. You have an outer function, which is my f, that 1/2. Your inner function is g. The derivative of this inner function is a negative 1, which I don't have, but I can put it in and counterbalance with a negative on the outside. And once I have that g prime in there, then I have all 3 pieces that I need. And according to pattern recognition, the only part of this that you integrate is the outer function. And the integral of a 1/2 is a 3/2 with a 2/3 out front, and the 4 minus x stays put, and then we had that negative 2 out front as well. So this is going to become negative 4/3 times 4 minus x to the 3 halves. So that's what the antiderivative is going to be right here. Okay, and then we're going to plug in our 3 and our 0. All right, so if we plug in our 3, 5 times 3 is 15, 3 squared is 9, so this is 9 halves, minus 4 thirds. 4 minus 3 is 1. 1 to the 3 halves stays 1, so this is just 4 thirds times 1. Now be careful here. If you plug in 0, you don't just get zeros everywhere. This does go to 0. This does go to 0. But 4 minus 0 stays 4. The square root of 4 is 2. 2 cubed is 8. 8 times 4 is 32. So this is 32 thirds. Okay, so again, this is a messy problem. It's got a lot of little things that can get you hung up, so be really careful. Once I distribute my negative across, we're going to get 15 minus 9 halves minus 4 thirds, and a minus minus becomes a plus. And then I'll leave the rest of this to be done on your calculator. I believe you get 7/6, so this is going to be 7 pi over 6. Okay? All right. So what we've been talking about is called the disk method, where when you take that cross-sectional cut perpendicular to the axis of revolution, you end up getting this circular shape which has a little bit of a thickness to it. So if that happens, then you can always use the formula volume equals the integral of pi r squared either dx or dy, depending on the orientation of your cut. What we're going to look at next is a variation of that method. So if you look at this next example, suppose that I take a little rectangle like this and I rotate it around a line that is not one of the boundaries of this. So in this case, I'm going to use the y-axis. So if I draw that mirror image over here, you're going to have this hole in the middle. And so this would not have a cross section that is strictly a solid disk because we have this hole in the middle. So what we can visualize is that there's actually kind of like two disks. There's this big solid one like this, which would have for its volume the integral of pi times, I'll call that capital R squared, and in this case this is going horizontally, cutting that y-axis, so this would be a dy. Then you have this hole in the middle as well, and what would be the volume of that hole, or that smaller little disk on the inside? Well, that would also be a nice solid disk as well, but it would have for its volume pi times the integral of a little r squared, and again this is horizontal, so it would be dy. So if I want the volume of this region, what I can think about is taking the volume of the big circle, the big disk, minus the volume of the smaller disks, and taking away that whole stuff in the middle that we don't want. So we're just going to subtract the big minus the small. And what this gives us is a new formula. The pi you can either put on the inside or the outside of the integral. It doesn't really matter where you put it. And when I subtract this from this, what I get for my formula is big R squared minus little r squared dy. And this is called a washer. This is called the washer method. When you have two circles, one big and one small, and you don't want the volume to include that inside disk, that smaller radius, so we subtract it out. So it's essentially just taking the volume of the whole region minus the volume of the whole. So what would this look like if we went the other direction? Well, suppose I had this region and I rotated around the x-axis, then the mirror image would look something like this. And if I take a cross-section perpendicular to the axis of revolution, we don't want the volume of this inside stuff. We want to cut out all this hole in the middle. So we can think of a big washer, or a big disk with a smaller disk inside, which creates this washer shape, and this volume would be pi times the big R squared, which would be this whole big radius from here to here, minus the little r squared, which would be just this distance right here. And this is going up and down vertically, cutting the x-axis, so this would be a dx integral. So both the big R and the little r should be functions of x, and the bounds should be x bounds as well. So again, this is called the washer method. One can think of this volume as being created by finding the volume of the whole region minus the volume of the whole. So let's practice a few of these. This is grouped in with the disk method because essentially it's just two disks being subtracted. So the disk method and the washer method are pretty much the same technique. It's just that in the washer method you're subtracting out some disks as well. Okay? So if we look at this next example, we want to find the volume of the solid of revolution formed when the region bounded by y equals 2x squared, y equals 0, x and x equals 2 is rotated around the line y equals x. So let's draw our region first. So 2x squared, that's a parabola. It's got a right half and a left half initially. Let's see if we want both sides of this or not. We want y equals to 0, which is just the x-axis, and x equals to 2. So the region bounded by those three things is just the right half of the parabola, the x-axis, and this vertical line. So we don't want that left half, so let's get it out of there for now. And now we want to take this region and we want to rotate it around the y-axis. So when I draw the mirror image, that left half does show up again, but it's coming from that rotation. So this is going to be a problem that requires a washer, not a disk, because you can see that we don't want the volume of this inside section because that's kind of our hole. So when we draw in our washer, our axis of revolution is vertical. So we always want to draw our washers perpendicular to the axis of revolution, just like we would for the disk method. So perpendicular to the y-axis means we want our washer to be horizontal. And it should look like a big circle followed by a smaller circle that would go from the part that you don't want, that hole in the middle that you want to take out. Okay? So here's what my washer looks like. Its thickness is along that y-axis. So that means this is going to be a dy integral. So we're going to want pi times big R squared minus little r squared dy. So we need to find big R and little r. So when I draw this in, we're going to need to know the center point here. We're going to need this rim point to get our little r, and we're going to need this rim point to get our big R. Okay? So the little inside rim to the center is little r, the outside rim to the center is our big R. Now notice all three of these points, they're all at the same height. So that means they all share the same y value. So all of these are going to be comma y. The center point has an x value on that y-axis, so its x value is always 0. The inside point is on this curve, which has as its equation y equals 2x squared. Now I can't put 2x squared in here because that uses x's and I need y's. So that means we need to solve this for x in terms of y. So let's divide by 2, and then let's take the square root of both sides, and you would get a plus and a minus case, but because we're in quadrant 1, that's going to be the plus square root case. So x is square root of y over 2 for that inside coordinate because it's on the curve. The outside coordinate is on this vertical line x equals 2. So what's the x value if we're on the line x equals 2? Well, x is always 2. Okay, so now that we have all 3 points, we're going to find big R and we're going to find little r. Big R will be the rightmost point all the way out to the farthest edge. So this point right here to your center. So this x value on the right minus this x value in the center. So 2 minus 0, which is just 2. Little r is going to be from the inner coordinate, so this x value here, minus the center. You're always going back to the center. So square root of y over 2 minus 0, which is just square root of y over 2. So now we know big R and little r. Let's plug them in. So big R is 2, so this is going to be 2 squared, minus little r, which is root y over 2, and we want to square that. And then what are my bounds for y? Well, we know that we're starting down here at 0, but it's not obvious how high this is going. To figure that out, we need to find out where the curve 2x squared intersects x equals to 2. So if our curve is y equals 2x squared and we want it to intersect x equals 2, just plug in 2 for x. So 2 times 2 squared, that's just going to be 4 times 2 or 8. So this is going up a height of 8, so y is ranging from 0 to 8. So there's my volume integral. Let's go ahead and solve it. We want to integrate 2 squared, which is 4, and then square root squared means the square root and the square cancel out. So this is just going to become y over 2. And if you want, you can think of that y over 2 as a 1/2 y. It's up to you how you think about it. So now when I integrate, the integral of 4 is 4y. The integral of y would be y squared over 2 times that 1/2 out front, and 1/2 times that 2 on the bottom makes this just become a 4. So this is going to become y squared over 4. And then we're plugging in our 0 and our 8. So if we plug in 8, 4 times 8 is 32. 8 squared is 64, divided by 4 is 16. And when I plug in my 0, I'm going to get 0 for both. 32 minus 16 is 16, so this is 16 pi. Okay, next example, same region that we had before, but this time we're going to rotate it around the line y equals 8. So let's draw our region again. It was that right half of the parabola intersected with x equals 2, and this time we're going to rotate it around this height y equals 8, which just so happened to be where those two intersected. So we're rotating this around this line. So let's draw in the mirror image. So it's going to look like that soup bowl again, but on the side. Since my axis of revolution is horizontal, my cross-section would be perpendicular to that, so it's going to be vertical, and I have a hole in the middle, so this is going to be a washer again. So my washer should have a big circle from the outermost rim, like that, and then our inner circle will be from the innermost rims, just like that. The thickness of this, it's intersecting that x-axis, so this needs to be a dx integral. So pi times the integral of r squared minus little r squared dx. So let's find our points. We need the center point, and I'm going to go back to the original curve down at the bottom, not the mirror image on top. So I want this inner rim point and this outer rim point. So I need these 3 points. They're all lined up, which means they all share the same x value. The center point is along this line y equals 8, so its y value is always 8. This inner point is along our curve, and remember our curve was y equals 2x squared, so the y value is just 2x squared, and that's in terms of x's, which is what I want. So I can just use 2x squared, I don't need to do any solving. The outer rim, notice, is on the x-axis here, so its height is 0. So our big R is going to be top minus bottom, since we're going vertically. So the top centermost point has a y value of 8, and I want to go all the way down to this point on the bottom, which has a y value of 0. So the big radius is 8 minus 0, so that's just 8. The little radius is also from the center point at the top. So use this 8 again, and then we're going to subtract from that the inner point's y value, which was this 2x squared. So there's my little r, there's my big R. Let's plug them in. So big R is just 8, so 8 squared, minus little r is 8 minus 2x squared squared. And my bounds for x starts here at 0, and this we're going up to that vertical line 2, so here the bounds are fairly obvious, 0 to 2. Okay, now to integrate. 8 squared is 64. We are going to need to FOIL this out, so that's going to give me a 64 minus 8 times 2 is 16, and I'm going to get 2 of those, so that's a 32x squared. And then 2x squared times 2x squared is 4x to the 4th, but all of that has this minus in front, so I need to distribute the negative across, so it switches all my signs around. And that means the 64's cancel. So what I'm integrating is just 32x squared minus 4x to the 4th, and the integral of that is going to be 32x cubed over 3 minus 4x to the 5th over 5, and we're plugging in 2 and 0. So we're going to get 32 times 8 over 3 minus 4 times 32 over 5, and when I plug in 0 I'm going to get zeros. I'll leave that for you to do on your calculator. I believe it comes out to 896/15 times that pi. Okay? All right. The next example here says find the volume of the solid of revolution formed when the region bounded by y equals 6 minus 2x minus x squared, and the line y equals x plus 6 is rotated around the x-axis. Okay, so this one would be probably a good candidate to use your calculator for, because it's not so easy and obvious how to graph this quadratic function here and how it intersects with the line y equals x plus 6. So let's pull up the calculator and go ahead and graph it.